Okay, so the next problem is an acceleration problem. Okay, so we need to anti-differentiate this to get to the velocity, and then from there they want you to calculate the net displacement. So the first thing I'm going to do is I'm going to say that the velocity is equal to the antiderivative of -1 over 2t minus 2 squared dt. Okay, so I'm going to work that out. Anti-differentiating this, I'm going to end up with, what is that going to be? -1t. I'm just going to write it like this. -1 divide by -1, so I end up with a coefficient of 1/2. Okay, and then it's going to be plus c. So then solving for plus c when t is equal to 3, the velocity 3 meters per second, so t of 3 is equal to 1 over 2, 3 minus 2 plus c. That works out to be, is that 3? Yeah, 3 minus 2, 1/2 plus c, and that's equal to 3 meters per second. So I get the c value equal to 2.5. Okay, so then my v of t function looks like this. 1 over 2 x, or t, sorry, t minus 2 plus 2.5. So from here they want the displacement. So using the area underneath the velocity function, we're going to find the displacement. So the change in d is going to be equal to the integral from 3 to 7 of 1 over 2 t minus 2 plus 2.5 dt. Okay, so then working this out, the change is going to be 1/2 log t minus 2 plus 2.5 t from 3 to 7. Okay, so working that out, I get 1/2. Plug in t into here, I get log 5 minus log 3, or sorry, log 1. Okay, and then for this part here, I'm going to end up with 2.5 times 7. What's that work out to be? 17.5 minus plugging in 3 in there, I get 7.5. And so I get those two parts. This becomes 1/2 log 5 plus 10. So that represents my net displacement, my change in d from t equals 3 to t equals 7. Okay, so here's some integrals, just practicing anti-differentiating. So this one here is not a standard integrals, so we can use an algebraic rearrangement or substitution. In this case, I'm going to use a substitution. Let u equal 5 sine x plus 1. That makes my du equal to 5 cos x times dx. Okay, there's my cos x dx. Okay, so I can divide the du by 5 to do a replacement. So the substitution then becomes 1 over 5. There's the du root u. Okay, well, this is a fairly straightforward integral. I get u to the positive 1/2 divided by 1/2, and that's going to be plus c. Okay, so then just simplifying this out a bit, that becomes 2/5 square root u. I'm going to replace the u with the 5 sine x plus 1, then make sure I have a plus c there. Okay, so this one here, this one is, we can rearrange it into sines and coses, which is an option, but I'm kind of noticing here that there's a cosine squared in the denominator. That's really secant squared. So I'm going to write it like this: tan x all squared times secant squared x dx. Well, that helps me out because the derivative of that inside function is a secant squared function, which is the outside. So I'm going to let u be equal to tan x, and my du then becomes that secant squared x dx. Okay, so then this becomes a nice simple integral, u squared du, and we end up with u cubed over 3 plus c. Again, replace that tan, the u with a tan. We end up with tan x cubed over 3 plus c. Okay, so here's some definite integrals. We want to find the area underneath this curve. Again, this is not a standard integral. We need a substitution, so we're going to let u equal x squared. Then du is equal to 2x dx. The 2 go to the other side, and I have my x dx on the outside, which can be taken care of by du. So I get du over 2, so I'm going to put the 2 on that side. Now that we're going to u, we have to make sure we're clear that the bounds are to do with the x's, not the u's. So then I end up with sine u times du over 2, so the divide by 2 is just on the outside there. So negative cosine u from x is 0 to x is equal to pi. We can put it back into x's, or we can actually convert the x's into u's to get the bounds. But we'll just do cosine of x squared, and then we're going to plug in our 0 and pi. So when we get this value, it's going to be 1/2, negative 1/2 cosine of pi squared. I'm not exactly sure what that is, minus cosine of 0, which is equal to 1. Okay, so we'll just plug that into our calculator to get decimal value here. We could just leave it like that, but we might as well just get the calculator value. Have a calculator handy here anyways. So cosine of cos squared is 0.985 minus 1, and then times that by negative 1/2. Okay, so I'm going to end up with this integral is equal to 0.007 units squared. Okay. Example 6, we want to find the area under this curve, and we want to rotate this volume. So this is going to be, let's see here. So when x is 0, y is equal to 3, we've got a horizontal asymptote of +1, and between 0 and 2 it's going to kind of go like that. So we want this area in here. Okay, so we're going to first find the area. Okay, so the area is going to be just the integral of that from 0 to 2 e to the x plus 1 dx. So we end up with 2 e to the x plus x, 0 to 2. Plugging that in, we end up with 2e squared plus 2 minus 2 plus 0. Okay, so the 2's cancel out, so we end up with 2e squared units squared. Okay, so we're going to take that same area now, and we're going to rotate that around the x-axis and generate a 3D solid. Okay, so we want volume, and in general, the volume is going to be the area. Okay, so the slices, imagine the slices, since we're rotating, the slices through here are going to be circular discs. So the volume of those circular discs is the area, pi r squared, okay, and r happens to be the height of that graph, which is y, pi r squared times dx, and we're going to do that from 0 to 2. Okay, so it's going to be, in general, area times thickness, or pi r squared times thickness. So I need to just algebraically do a little bit of rearrangement here before I integrate that. So I'm going to go pi 0 to 2. It's going to be 4e2x plus 4e to the x plus 1 when I square that all out times dx. Okay. This antiderivative is going to be 4e to the 2x over 2 plus 4e to the x plus x, and that's going to be integrated from 0 to 2. Okay, so that will give me the volume. Plugging that in, I end up with 2e to the power 4 plus 4e squared plus 2 minus, okay, plugging 0 in, I'm going to end up with 2 plus 4 plus 0. Okay, so I can simplify that a little bit. It's 2e4 plus 4e squared minus 4 units cubed is the final volume.